Fakher Assaad, the University of Würzburg, and we're telling us about the first time it changed on culture. Welcome, Fakher.
Thank you. Thanks, Théorie. Can you take Joseph away? To figure out. That's it. I'm good. So thank you for being here and thanks to the organizers. Very nice. Okay, so I'll talk about state change in Kondo system. And it's Kondo systems are really experimentally relevant. So all this comes from experiment is what we're doing. And they map onto U1 gauge periods. So it's a very nice way of realizing gauge periods and understanding the physics from this point of view. So I'll start with Kondo systems because that's experiments, right? Experiments and models, field theories. And essentially the quantum Monte Carlo, which again we're talking about before, is a way of summing up, all the gauge fluctuations, etc. That's the way I like to do it. So the first part of the talk will be a state chain on a metallic surface, right? And depending on how you choose the metallic surface, the Dirac conformal with the half-filled fermion surface, then you get essentially a lot of the states you get in Kondo systems. Right? You get Kondo breakdown transitions, dissipation, and magnetic order and disorder transitions. So this is the type of mini personal type transition that you can realize in these systems. So I'll talk more about this. And then it's time allowed is the second part, which has nothing to do with the first part, which is exotic quantum criticality in the Dirac system. And it's a nice little model where, so this is a full model, no experiment and nothing for the moment. And where you have a loss of the third transition, but only between two metallic states where only 2 out of 3 cones get gapped out, right? And then there's another transition in this model, which is order transition. So into somehow you could find upon criticality, but there is metallics with fermions. So that's pretty. We just have some data. That's all we have. Okay, so let's start. The people who have done the work are listed here. The people who are in this course. So Maxima Dubsky, with your Sarko, and Zion Group, they all work on the common stuff I will show you. And Zion is the one who works on the Dirac system. And then we have some internal collaborators. So we have Kevin, I suppose, with navigants, and then the leader who works on organization to get some work for the participation and use stronger environment. So let me start with Kondo system. And the experiments we have in mind are just a copper 100 surface, which you capture with a small insulating copper nitride surface. And on top of this, you put a cobalt atom. So the cobalt atom has a spin P amount. And because of spin orbit coupling, what is allowed interaction basically this single ion atom and it's squared. And it turns out at this point the system G is positive, so you have a split between the plus one 1/2 doublet and the plus one 3/2 doublet. So that's important that the G is positive. And so essentially the low physics, the low line physics of this cobalt atom on the surface is plus or minus 1. And then if you look at SPM, so what you do is just put the SPM probe on top of this cobalt atom, and you'll funnel through the orbital of the cobalt atom. What you see is a nice Kondo residue. This Kondo residue is the peak here, but if you put a magnetic field here, it's split. And this transition, this bump is for the step here, is the transition from here to the 3/2. So you will see the new channel with something like that. So this is something we can do. Which is actually not so easy to find such a beautiful Kondo system experimentally. You talk to explain people, it's always a mess, right? And this one is just actually, the more you talk to people, the more you appreciate this talk. Not my fault. It's just extremely smooth. So the Hamiltonian, how you simulate this is very simple. You just need some induction electrons, and we'll use the copper metal. You need a spin 1/2 impurity. This when you concentrate on this energy, you get this. You get the spin 1/2 degree of freedom. With Kondo couple, Kondo has to be positive, but that's a non-Kondo effect. Locally to the spin density next to the massive spin, then we have the magnetic. I'll come back to what exactly we calculate, but essentially I would like to argue that Kondo is somehow an inverted composite fermion. And the composite fermion we'll see is basically this is the Kondo resonance. So when it comes to the temperature, this will be the composite fermion. I'll talk more about this later. But essentially, what Kondo is telling you is that as a function of temperature, you generate a composite fermion, right? And this composite fermion is essentially the Kondo that you see. So this is just for Kondo. We know a lot of this. What's amazing with these experiments is that you can build chains, right? So you can build chains up to nine cobalt atoms. These are chains which are open, so there's no translation symmetry. And when you build up the chain, somehow, or even if they don't really understand very well, you generate a Heisenberg coupling between two cobalt atoms. So this is not, the claim is that this is not an Arctic combine, that there's a coupling via the substrate. And you can actually, so I don't really care where it comes from, you can just really measure it experimentally. If you put two cobalt atoms, then you'll see that there is a gap at zero. You're getting sort of this gap here, with the order of 0.02 kiloelectron volt, and that gives you sort of the single crystal splitting, and that gives you a measure of the rate. So the model you have to simulate to understand what the experiment is doing. The one before the single impurity has more than one impurity, all goes from 1 to 10, and then you have a Heisenberg coupling between the two, and you have a rate. And sure enough, if you, yeah.
You said they can only go to 9 atoms per chain link. Why is that?
Well, okay, so the way I understand it is that the copper nitride are small islands. And so the islands, they're not so big. And so they're limited by the size of the island of the copper nitride. If they don't have the copper nitride, then the cobalt sort of goes into the copper and it changes the character of cobalt. It's different. So really the copper nitride, it's very, it's tricky. I don't know what it is, but it's a lot of tricky. Yeah.
Okay, can you see the blue kind of diagram, the gas spectrum, how are the changing as the number?
So this is basically what they do is that they look, this is experimental data, and what they do is they what they have a magnetic field, they have the magnitude divided by the biopole. So this would be the common reference, and this would be the split of common reference. The common reference and the split of common reference. You put two of them and you can put the tip on the first half and the second half, because there's a vertical symmetry, they're the same thing. Here you have a magnetic field of each common reference. I don't want to go into these tips, but then you can do this. Then for 3, you have these two are the same, so there's something different happening in third. And and we can show this. We can really go and look at the zero bias model in a really small model, use the Monte Carlo and really match it to this. It's amazing, right? So that's what I want to show you. But these Monte Carlo is amazing thing. Always happening. Maybe they do real stuff. Very tough to experiment with. So really fascinating. So this is them here. But of course, the aim is to get rid of these finite chains and to do infinite chains, right? To see what happens to the premium happening, on the accounts. That's it. So what they could do, instead of, they could just build a ring, right? Our simulation is basically the 16 happens. That's not so big. But what we need is translation symmetry, right? So they could build a ring, that would be everything. So that's the motivation. And so this is the model we have now. So we get rid of the field, and this is the model we're going to talk about. This is a Kondo model. So you can think about it generally as a metallic thing. Some impurities are a different graph. And you want the conduction electrons, and then we have some Heisenberg interactions between the impurities. So that's the motivation of the model. So how do we do the numerics? I'll go now to how we do numerics and try to understand the phases, classification of phases of the Kondo model based on the pattern, right? Based on the V1 pattern. So how do we do this? How do we simulate it? Simulate the freedom with the fermion. So if you just start up the simulation instead of going to work with this 10 degree of freedom, do a world line for this 10 degree of freedom, take the fermion, we couple with that will work with us. You have to find some tricks how to combine states in the quantities. You want items to do the quantity, how to combine it with the fermion. So the way we do it is fractional the particle, correlation for the states. So we got fermions, they have constraints, and so that's a state. Okay, so either you can, once you agree to do this, you make exactly, there's a one-to-one mapping of the way to graph from here to here. So this is like hybridization, and and if you square this, you square the two things like this, do the calculation, you keep your report that you have this rate, you will fall exactly onto this model, onto this. So that's exactly it. The same thing for the Heisenberg term that follows the heat is on the ball. So the Kondo is on the side somehow, and the heat is on the ball. The variable afterwards, you get the alternative. So this is just an exactly writing. Of course, when we do the Monte Carlo, we won't be able to constrain over space. Over the sampling, we have to do the constraint with some type of energetic. So we put in the Hubbard U, and we'll say that the Hubbard U has to be big enough so that we have no velocity. So this is not so, we'll have to put in the code, when we write the code, we'll have to put a number for this, in front of this number is big enough. And the crucial thing of this approach is that this term here, or this term here, basically commutes with the Hamiltonian. Because essentially this is the parity, right? This is the parity on the X. And these things, because it change stuff, right? But they don't change the parity on the X. So this Hubbard U commutes with this. And that essentially means that the constraint is imposed to the efficiency. And what it means is that you can, before you do the simulation, you know that the constraint, the double occupancy, if you want, minus the 10 to 2 here, will go down exponentially, you know the law, you know the free factor, you know the law, you minus the So if you do the simulation, you get exactly this, and you know that everything is okay. Yeah.
So if you turn on the JH, because it becomes a periodic model.
The periodic Hansen model has a different model.
That reduces to the Conformal model.
It's like,
That reduces to the Conformal model.
well, it is. I'll show you how we got it. It's not so good. Yeah, but how do you get? Yeah, you're right. This is like it is like Hansen model. We're going to reduce those triggers in Hansen model. How do I see here that I have? What is the object here that's participating in the logical bond? I think that's not so easy, right? Do you agree? So that's that. So there's a whole lot of big work. But essentially it's enough. Some of you there. I'll come back to this later. Okay, so I can come back. So how do we do the Monte Carlo? Monte Carlo needs some coverage knowledge. And we would need because to decouple this, we need two real fields. And those two real fields here, we will combine them into a segment. So I can use this, right? So this will give me my what I try to do with all of it. Okay, so the B is a complex variable, right? For the to decouple. Then I need also per bond and complex variable where I get the thing is right in this form. And then I need a scalar, A0 for the other. So if you just take it along, and I think that's it. That's pretty. So you will get a lot of terms. You will get you get the square term, square term. There's one term which you should also get is an A0 square term, and then you one over two. And the one you are going to put it to infinity, and so it goes to zero. That's very important because the A0 square term is this term that breaks the U1 gauge. So you have to go to infinity, and then so these are these terms. This is now graphing variable, the very big, the hoping, essentially this is encoded into here, right? And then I have this is the now it looks a bit more like Anderson model. We have hybridization, but it coupled to the complex. So the detail has more, but not the detail also okay with us more fire. And then here, what we have is then the same thing, but for the electron, the fermion, essentially is going to be one gauge. So you want gauge to be one gauge. Okay, so far so good. So now, the Monte Carlo we do essentially work with this activity. And that's the ability for Monte. What you do is that, well, you have those fermions integrated with fermions because you have the positive transformation. everything is bilinear, so you can integrate them out, and you will get a determinant. Now, the determinant, so this is the log minus log of. So, if you look closely to this, you see that you have SU2 symmetry, right? Because all these are spinors, right? So the spinor, everything is like somehow SU2 symmetric. What the SU2 symmetry tells you that this determinant factors out into a determinant just in one sector to the square. Now, if you then you have to work a bit more, but if you assume that it has no chemical potential and you have a Tij, which is a particle invariance, and you need some constraints on the J, etc., then you can show that this determinant is actually the determinant in one sector is complex conjugate to the determinant in the other sector. So you have no cycle. So this means that this object here, that's in here, that's what this here is something which is positive, and so I can do some simple Monte Carlo. And the Monte Carlo we do is just to sum over all the H. So Z, that Z should be the high. Actually, this is the wrong error. Then this Z should be the high. And then the B, that's this one. The R, that's this one up here, and the A0, that's for the region. So that's what the Monte Carlo is. So
You don't need, spatial?
oh yes, the A0 tau. Everything is a tau. So this is a A0, this is space and time dependent.
It's not the time component of the
So that, sorry, the gauge field you want, so this should be a cop, right? The vector part of the gauge field comes from the imaginary part of the cop.
Okay.
And the A0 would be the part of the comes from the so we have a code which you can download and try to make it work. It should work. And it's pretty fun. It's how to write down. So think about it. How do I write down a Hamiltonian such that anybody who gives another Hamiltonian can repass it into the Hamiltonian, right? Okay, something like that. Because that's everything. And so our claim is that if you give me if you give me the generic quantum chemistry problem, the problem that I think about interact, etc., then I can write it all the way down into a sum of parts. Very good. Right? So essentially, the code we have is looks complicated. Maybe it is a bit complicated, but you have terms which are just one body, then you have one body to the square, right? So that's obvious how you make it work with the Hubble topology. That's important for us. And then what we need, if you want to put in Z2 gauge theories or something like that, what we heard from ZI, also last call, then we need to have some type of dynamical variable with the rising spin. It could also be a Kondo, something like that in our code. So it can be a discrete variable, it can be a continuous variable. We call it the generic one body operator and then Eisen. So this is the dynamics of the Kondo or the dynamics of the Eisen spin or something like that. So that would be for example, the Fox term, H term, something like that. And this would be the So it's all the models which the ZI was showing, the fermion models and the model showing here can be simulated with this package. So it's pretty fun. So and the people who are it's really like that is because you keep contact with us from the students. The analysts were working this on a regular basis instead of the practical and the virtual the last week I think etc. So it's pretty fun. Yeah. You might I mean, I don't know if you have fun talking about actually taking off for fun, but actually I think it's fun. So let's get on. So Kondo system, conservation laws and gauge. So you have a U1, you have a global U1 conservation. Then the C has the electron has a charge. And so the global U1 conservation law and the gauge transformation, global gauge transformation by the side phase. Then we'll have to compensate it by shifting my phi for this alpha. And this only comes from the back. So the phi is the phase of this bosonic mode. This bosonic mode is like a hybridization, so it also carries a global. That's not so interesting. Well, it will be afterwards, but you also get, because you have no A0 square term, you have a local U1 A0. So the locally one gauge grams is given by this for the F. I don't change the C to a local gauge transformation for the S. And then I have to, do the gauge transformation for my vector potential, which is here, and then also a gauge transformation for my plot. Because again, this here carries U1 charge of the F as well as the global charge of the C. So this is so this I can use now to define the basis of my Kondo line. And for me personally, the hardest thing to do is to define what people will think is the simplest possible thing to define, right, based on this. Now, so what I'm finding is that there is the Kondo heavy fermion case is basically an emergent composite fermion. So you have this F, this has the U1 local gauge. Right? So basically F, if you try to measure the after you measure F factor I, and then it's basically 0. But then if you compensate this with the phase of this E here, and this basically compensates the U1 gauge factor, this remains there, and this offset requires that you want also because this has an electrical charge, this offset is that firm. Right? So this is the Kondo effect is essentially emergent. So because F is an electron, essentially it can become a fermion, right? And if you generate that in the fermion, it will be a Fermi surface. And if you now say the Fermi, it will also participate in the volume. And that's how you could easily understand why in a present fermion metallic state, you can count both the F electrons, the composite fermion, as well as the motion electrons for in the summary. And then finally, so there are a lot of that's the way I see it. I mean, a lot of I guess it's a big mechanism, like in the water, I mean, it's by the frozen, and when you say that to give them that work, but for the metal lab, I can always find one of that. It's actually you say that F requires a charge and uses S. I don't know how to say it. Essentially, but it's free when it comes to numerically. So you can do these, the nice thing of these Monte Carlos is to really check all this, right? So you can say, well, let's go into your code and measure the correlation function with these F's, right? So this is the Fourier transform, and basically the occupation of the F in the phase space, and you will get something with this plot. It will be perfectly okay because these F, you don't have a filter on it, you have a one chart. And of course, this F tilde here will be measured this quantity in your code. But just multiplying with this complicated target from the public boundary field, then you get some dispersion relation and you get this end of the smooth. And in this special case, it's smooth from square lattice, and you have exactly one electron per conduction electron, and that's the so you essentially give the electron out. If you look at the composite object, exactly one composite electron on the side, and then the conduction electron to the side, so you have two electrons in each cell. That's a condition for an insulator, and that will be your Kondo insulator, and that's what is F here is a smooth function. Right? So the Kondo insulator is a simple thing, it's a band insulator. Taken from the point of view of the Kondo lattice model, it's a band insulator because you have derivation of Kondo. That's the thing. So to go on is this composite terminal and tilde is something which is only really defined in the past after you get the past integral. And so you would like to go back to operator to be able to pass it also with D or something. And you can in this paper you can argue you can argue that this composite fermion is proportional to a fermion side of I, if you want, which has this one. And for your this form also has something different origin also and Théorie and also Peter Coleman. Essentially, you do the typical transformation of the D electron, right? So you will get it after this. So that's just the composite terminal is just a suitable transformation of the correlated electron in the energy.
So this carries spin.
So this carries, yeah. So this carries, so the F carries spin. Right? So this carries the spin, but no charge carries it. Right? So this object carries spin and charge. And this transforms you back like front. So this is the front. So when you want to, when you want to calculate the Kondo resonance, you just calculate the simple spectral function of this object. If you want to understand altitude on the square line as a function of temperature, this is the spectral function if you want of this composite fermion. You will see that as a function of temperature, you generate this sort of channel here, which that would be essentially that's very similar to what we have shown before. Temperature, and all of the formation or the way that the composite object when you lower he was taking at zero temperature. A Kondo breakdown condition would be at zero temperature. You have this composite fermion and somehow you just destroy the fermion. It's very interesting transition because you block some of the parts there. You divide with some other people volume. You see that with topological order to understand this.
What's the gap scale?
The gap scale here is available. The gap scale is J. Right? This is a common insulator.
What value?
Here I use J equals 1.
It's not one.
It's 1 divided by 4. It's 1/4. I saw that in probably divided by 4. Sorry, it's good close. I don't know. Good.
So then you see that immediately, like, you see this happening, formation of the also start.
That's not so clear, right? I mean, for the same group, yes, for the balance, it's not so clear. For example, in this paper, we were very surprised to see that the way that particle density of the pull, the weight of this thing, is not the Kondo scale, it's the one J. So it not does not relate directly to the scale. You don't look up directly to the scale of having we claim that there's some energy effect. So take it. So it's not going to take that from the single material into the
Sorry, if I may ask a question.
yes.
Sorry, Fakher, I'm sorry.
Go ahead.
Sorry. I was a bit fast. So what's the difference of the spectrum on the left column and the right column?
The left is the spectrum of the conduction electron. This is the right. This is the right. This is the conduction electron. This is the heavy burn. This is the F electron. So this is thank you for the. So you see, in principle, you're measuring. In principle, you have a if you put a just measure anything, any citation with the quantum numbers in the electron, right? So everything you see here, you see here, you also measure the quantum numbers of the electron. That the spectral weight is very small. I don't know where to look at these. So essentially, if you believe that we have some spectral weight here, right? We would follow this one, but then it's so small that we don't really see it. But so you want to pick up the heavy thermal character of you much better by measuring the heavy thermal. It's composite thermal. Is that okay? Yeah. Just conduction electron. And also the conduction electron, if you go to high temperature, you'll see the same. These temperatures and it's pure light. The composite fermions now at a constant temperature, this is many bodies. Yeah.
So just to make sure, it looks like at the lowest temperatures, those conduction fermions are getting to the gap out.
Yeah, they're gas out. So you base that. They're gas out. So you generate. So what happens is that you generate your composite fermion. The composite fermion is a simple electron. You are exactly this. You feel like filling the one of the damage. That's it. So you have the Kondo insulator is a simple gap, is a simple band insulator. Triple band is a triple state matter. When you don't know is that the object of the electron is complicated. So that's where when Pierce talk about I'm recording, I won't say anything. So that's why I understand the little Pierce of different so these are the phases. So I took a lot of time for the whole. I think it's the hardest thing for the big side mechanism and what of it. Then there were other transitions. We have the next W, so we condense this, we have more H chart, the vector, we do that. you can do this in two ways. You can use this but not have a, not have any, not have color effect. The game, you still have a game that you can define. But if the NW thing, you can have Kondo plus NW. That would be something which is possible. And so, and then, Kondo breakdown, there is basically, a transition which allows you to into this, you know, this, and this, something like that, right? Sorry, so, yeah. Something like this. And so this would be, then you also have FR cases, which will put forward a central, by myself, et cetera, where, you essentially have no common effect, and you have no analysis, you depending on the number of particles you have, electrons you have to unit cell. This has to be the problem with the water thing, otherwise the problem is the volume. We also have a problem that as you go to start, they have temperature in the water.
Sorry, okay, so for the billion and W star.
Yeah.
The connotation pattern is the same.
Yeah,
But,
yeah. So I think,
it was defined.
yeah, that's a possibility.
But it needs, it's condensed,
In the physics condensed, you do things,
and the colors are fine.
all of them confident,
You can have find them without connotation.
depending on,
Just,
depends on how.
yeah,
If you get, so if you think about, so, okay, so this is a big place, so there's a long folder network, so.
that's very model.
The NW, so the NW is, the NW structure, that means that you should be able to have normal.
Yeah, the SW, monopoles,
Ah,
events, and then you know, like there's the
yeah, yeah.
SW.
So this is the thing which, basically, so if you go from here to, if you go from here to here, right, you basically have to find, we support it, you know, the terminal.
The full number remains.
So the claim is that, aside from these phase, aside from this phase, we claim that we can get all these phases somehow, on these spin chains on the house. That was the aim, I don't know what I'm doing. Okay, so now let me start with the first, the spin chain on the outer surface. And so this work, the reason I did that was very interesting because we started a long time ago, and it was it's a hard thing. So I met that in Théorie with and collaborating on to work with them. So this is a model, we know it, and we just take the firms. So we can look at limiting this. So if JK gets very big, then it's somehow a trivial state. The JK equals infinity and JK won't be different things, you have to be careful. But you essentially see that you know each spin factor is not only one the same way, and that's something which is rather well understood. You might understand the water that spinning the screen, but you know, electrons, the physics of the whole method. Right? So this is something. Now, the hardest thing is what happens at weak couple. How do we go about this? And so what we do is take, you know, integrate out the formula. We say that JK is small, so we can do perturbatively make integrate out the formula. And so we have how to go. The next thing is the second term we get is the second order in JK, we found the determinant is basically a retarded interaction. And this is because between the spin between states. And then retarded interaction will be essentially the spin susceptibility of the host matter. So now everything depends upon the form of it. And if you have this type of Fermi spaces, you put in your thing in this direction, other chemistry, if you put your thing in this direction, then you will see that the time zero of R, 0 times the one of R before. So if you just take this, just put the time equals 0 here, and just look at 1 over R4. And if you look at, is this term relevant or irrelevant at, you know, the fixed point of the one-dimensional thing, where the scale dimension of 10 is a half, then you'll see that it's irrelevant, right? So you can get rid of it. So now what about the time element? I take away I say equal time, equal space, which is equivalent to time. This goes as 1 over tau squared. There's the next thing that is correct, there's the long square, because the next thing is the number. And so, this was a 1/tau squared, and this turned out to be marginal. So we don't really know what happened. That means that if I put a metallic, if I put a spin 1/2 chain on the metallic surface, I have a coupling which is marginal, and I have to solve another problem which turned out to be non-trivial. And this other problem gives us a detour, right? So that's why the problem was so hard. You have to go somewhere else. But you have to ask the question about a spin chain on, locally coupled to an ohmic path. These are just words, which are telling you that I'm just going back to my previous thing here. I'm forgetting about the spatial dependence of this, and putting it here, and putting this relevant to renaming the local temporal thing, and that is essentially what we have. So here's the question. What is the physics of this system of spin chain locally coupled to an ohmic path, and that has something to do with spin chain on a metallic surface. So this is where Manuel and this is happening. So this because Manuel, this is just a problem of the boson problem. In Manuel, sometimes we will develop the basic part of code, an SSC code for retarded impact. For basically, and there's SSC code, but with some retarded impact. It's a very efficient code. We can solve it. Okay, so let me go now back to get an understanding of what happened. Go back from the topic to go to the model. The model you really try to here is this. We have your spin chain, the quantum spin. These are bosons, right? When they set for each side of the boson, with a Q, and the first one with a Q, and they couple like this, which is a vector of three orders. And the only thing we really need to get this tau squared is to be put at the spectrum of the J level. That's going to be the proportional to omega, that is the omega. So the first thing you should do, I ask myself, and it is evidently yes, but can the bath screen? Right? Can you screen with the bath? And the answer is no. The bath cannot screen because there's a conservation law. So then you just take one section, and then forget about this part if you want. There is a total angular momentum, right, with the bosons, plus the grid one now, right? So that's the conservation law. And so this is something integer, this is half integer, so you will always get a half integer. Means that that's something which is conserved, meaning that the bath cannot very expensive out of these bosons here in this. That will always say half integer. The only thing with this bath will do is to make it want to spin more, show the freedom to make it spin less, will not fluctuate so much because it's directly kind of goes. So that's the mechanism that will recode in this order. Right? So we cannot screen, so we'll on each site, we'll always have a spin 100 degree. And then when you couple the sites together, we'll have to ask the question, what they order. And so,
Question, because initially, you have these fermions, spiralis, which can't screen.
Yeah, but
here.
okay, so
no, they cannot screen.
Because I'm just going up to square.
Yeah,
I'm just stopping everything to the J squared. I'm just doing tractable and stopping at J squared. So that won't screen. That won't be screen order. Really will come out because that's the first thing comes to the order. Then there is no screen. That's so that's what it is. Okay, so that's one. But these are the simulations that Manuel did, and they are already hard because essentially because they have a model model. So what this is a correlation ratio. So you measure the spin state correlation along the thing, right? For you transport them, and then Q equals 5 here, and so this correlation ratio is found in the have all order. It diverges, it does not diverge as quickly. So along the order is 1, the order S of Q is the smooth function, delta Q is about 2 pi divided by that. Small, it's long wavelength. If you have something that's flat, then it's 0. That's exactly what you want. But nice, it's an input, you know, like this is looking very important. This is very nice to go with or fill it out. So here are the results. So these are different values of different values of alpha for different sizes, etc. You see that for big alpha is something down, then this goes up, right? So it goes to something with order. And then when alpha is small, then it goes down to something like this order. And so there's a crossover, which is a crossing between those two different system sizes, this one, etc. And what you see, which is typical of something that is really marginal, is that this crossing is always shifting down to lower alpha. So it's slipping away. This is the worst thing that can happen to you in there. Right? There's double system size that moves, so everything is sort of everything is not that much. So this is what you're learning here. But the other thing you can do is plot as a function of one over out this correlation ratio. You see that as a function of system size for different alpha, there's a characteristic length scale where it first goes down and then it goes up. It goes down and it goes up. So this is a length scale that you want, where beyond which, right, right, correlation ratio goes up. So beyond this length scale, then you would see some type of long-range order. So if you look at this length scale and you put it as a function of 1 over half, probably you see that. Right. So it seems that to resolve this ordering, right, then you exponentially large lattices, which is okay because the operator. But at the end of the day, you see some type of ordering with a distinction on the method. That was the result. Now, this is a quick understanding of the result, and also to tell you what you should expect from the dynamics, right? The spin dynamics. When we look at the spin dynamics of the chain on the metallic surface. So let me start with an order parameter. So Joseph was talking about fourth grading, etc. So I will just take fourth grading order SO3 or the order parameter of time over 20. And this will give me essentially that will give me a description of my high order chain. I'll forget to talk about the front because we will order if I can do that. Yes. Yes. So I'm fixing out. Right. That's how I do. So let me take this one. This is the smallest column. Then it goes down, right? And then boom, it starts going up. So it's a characteristic length scale, which tells me, there is a nice scale of the operation starting to see on there. And so what we're plotting here, so this is 1 over R, so this is this length scale. This is what we call LC, right? And we call LC as one of the lower alpha on this anyway. No. Yeah, but there's no other one. There's only one.
And that's because this is still just the leading order.
Yeah, this is So what I'm doing is I'm defining. So this is kind of it's not very common, but I'm starting with something, and this is the leading order. The leading order is defining a new problem. Right. So it's kind of solving a new problem.
It's alpha basically being good.
Yes. Right. So alpha is the problem. I'm defining a new problem. Solving the problem comes out. This is it should not be done in the past. So I did that, but you gotta. So this is, I'm still working in the detour. There's a detour. So I'm not really to the point. So
Yes.
I have 10 minutes. Okay, so this is the result part. This is the way you can understand this. And so you have your order parameter in one of these equations. You assume that I have a long range order. So long range order gets my O3 down to O2. So I have order in the Z direction, sigma is very small, and here the transfer fluctuations. So I'm going to plug this into my S and do an expansion. And the first term looks like this. And then I have to find over. If you look carefully at this, then you will see that. Well, if this is still in here, it's still R divided by R, power is minus square tau. If this is the 2 problem, then this thing will be so this stays scaled in there. So if you put yourself at the scaling variable point, then you will see that all the higher order terms will be So this tells you that this should be something like a stable fixed point, and it will describe, not have that. So you can do this way, this is a very short way, or you can do also a full spindle calculation. With this paper, and what you will see is that the spin is a number of spindle calculation. You see that only the square. But so we know what's happening. So now let's go back. Now we go back to the problem we have at the beginning, and defining it that as small data, then we can use the result as before, a long way of going, and then a small data, a big data, we have a complex information. We want to go to the sort of thing. So the claim is that it's a fascinated type condition. So let me go through the data. So now we go from, before we were with bosons, right? So with bosons, you can go these type of days, we refer to what the problem here is that you have a sequence 2. So Z equals 2 means that you have to go to extremely low temperatures to do that. That's extremely expensive. It's not working very well. You have to be pretty low, like we're working very much. So now we're working with fermions, so we're, the data, the algorithm is from low. So this is the free energy of the function of J. So this is now the full model. And we see that there is a transition of 3.1. And we try to see how to, what is the dynamical exponent for this transition, but we will need to do some theta, to scale theta with now we need the dynamical exponent. So what we did is just put ourselves at 2, right, close to the critical point. Look at the 1 over spin state correlation along the thing, along time. This is like 1 over r, and along this is along the state at equal time. This is at time at equal position, and we see the 1 over the power, which is really z with the order of 2. So all this is very timely. If this is equal to 2, if you have the z which is equal to 2, then I can go back to my correlation data, and I know that this should be a real preserved quantity if I scale correctly my size of that, and that's why I need 5 minutes. So this, we know this, and so we see that. So this is where things are hard, right? So we claim, first data record, working on that there is a crossing point here, right? And that it's awesome. It's hard. It's hard. You should respect it. And then you notice how they go up, and then it's too small, and we just So we claim that there is some kind of order. This is remarkable. This is the spin dynamic structure factor along the chain. So this is the free chain, and you see very nice relations along the chain. This is below the transition, and you really see that the 2 spin on the lower and the 2 spin on the space where it gives you some type of run and you expected. This is at the critical point. And then this is in the metallic phase. And essentially the metallic phase, you should understand is that it's again the formation of this fermion. It's called the fermion, but it's not the fermion from the electron. This is essentially you don't have a lot of weight, you just have to weight here, but it's not so much weight to the particle bubble if you want to copy this thing. You do the calculation, you get very little work. So this is something you can do. What else we want to see is that what type of phase is this? Right? So there's an orderly sort of transition. We would like to understand does this tiny fermion or this composite object, does it break down across the transition? So what we calculated is a special function again of this composite fermion. So this time it's a metal, and you see that in the ordered phase, and I have these very short bolts here. This is my composite fermion, but I will claim that because of very sharp signatures here in the spectral function that I still have some not situated. So let me take one point here. We have other models where we have a Kondo breakdown. And the Kondo breakdown is how do you see that numerically? Basically, in the Kondo phase, you see the code. And when you go to the Kondo breakdown, just incoherence. So I can see some type of goal here, gives us some good idea that we have this functional fermion object as well, which is the one. Yeah, but yeah, something to change. Perfect. And then this is in the order, this is the fermion. So that's it. For a we have a type of order disorder of transition in a system which has dimensional mismatch. There is no Kondo breakdown across this transition, so it is complicated fermions, which sort of requires some kind of ordering across the critical point. And so it's it's sort of a mini type calcium type transition, which is simply principle that but these are just like one of the big diagrams. But I did not show you, I won't show you either right now. If you change now if you put the spin change instead of putting it on the Italian surface, you put it on the semi-metal, then the whole picture changes. The front thing that we can follow the same thing as the metal. But instead of having this anti-correlated metal, you will essentially have a decoupling, if you want, between the decoupling between the spin degree, the freedom, and the project. So this is a Kondo breakdown. So we can have a Kondo breakdown transition where the composite terminal here, the composite transition breaks down, and here we have a transition where so that's what that was the third part of the book. I think I'll stop here. Right? So the only conclusion that I can we got very interested in this. They're extremely rich. That's my only thing. That's the only message I want to have. These spin chains on the Italian surfaces are a marvelous something which is easy enough to do simulations. It's still very challenging. You don't have all the results. You don't know this. You don't have the ability for this either. It's Kondo breakdown transition that's maybe easier than conformal invariant. That is equal to one, maybe more, but maybe easier. But aside from that, you don't have so much information, so you can do much more. And it's also there's a real possibility of doing this experiment. You can motivate those people in help to do those experiments to try to do bigger changes. You can change the days by putting the atoms at different places, etc. So they really have the possibility of doing this stuff. Okay, so I just switched to the last one, which I'm here. This is the last thing. I think Lucas will maybe talk about some next week, right? Sorry. It's Zoom coming. That's a new word. It's Zoom coming. And I am locally coming. I'm physically here. Okay, yes. Okay. Yeah. Okay, so thank you.
Actually, can I ask a question?
Yeah.
Yeah. So
Thank you.
actually, so you simulated the spin chain with like a non-local interaction along the time direction.
Right.
Yeah. So there was some simulation by Sandvik actually simulate like a spin chain with non-local or spatial interaction. So I wonder whether you can see like a space-time symmetry. Like so do you find a similar phase diagram as we did, or?
So I don't know what Anders did. What type of, was it a long range? Was it a power law? What was it?
Yeah, it's a power law. It's a power law interaction.
Of course, if the power law, depending on the power law, at one point you should get long range order, right?
Yeah, right. So here, sorry, I missed that. So here you got a long range order as well.
Yeah, but it's because of dissipation, right? Because of in the imaginary time direction.
Yes, right. So the origin of the long range interaction is different, but I feel because supposed to be perturbing a CFT, actually the space time should be similar. So
No,
yeah, I mean one should expect to see the similar physics.
So what is the question, Chenki? It means that if you would say that the phase transition which you take by coupling in the imaginary time direction, and let's assume that you can change the power of the bath.
Right.
This would be the same criticality as if you take that in real space and you change.
Yeah, I think
Yeah,
something similar phase direction.
Yeah, that could be. I
Okay.
agree. That could be.
Okay.
I did not know of this. I'm sort of talking to nobody. Can I see you somewhere? No, I don't know.
I can hear you.
Yeah, we can hear you. That's Cenk is, I mean,
He's everywhere.
he's everywhere. Cenk is everywhere. So yeah, I don't know. I don't know if this should be, I guess it should be the same thing, but I don't, I never thought about it.
Yeah, okay, yeah, thanks.
Is that, so,
Consider the share. So I have a question about the choice you made for the chain alignment, because you said you take the necessary purpose
yeah,
for the coppers,
yeah,
then you put the chain along the X direction.
Yeah.
So how much of that influences your planning? Can I sort of yoke away and have not nested and?
so if you go away, that would be the same. The fact is that the orientation is actually pretty important, because if you, so if you put the name like this,
Yeah.
you will take this power.
Mhm.
Right, so it's, there are fun grammatical effects.
Yeah.
But both become important, depending on how you do it. So maybe check it, that's maybe an answer to the question, right? But I can't change this, because this is the time, but I mean, depending on how you put in the chain, right? Then this, I just know the limiting this direction. You need it direction, how many times, that would be the calculation. So that's one of our questions. I'll go from there from one to the other one. But that would certainly change.
Yeah, for experiments, the first purpose
Yeah. So this
is not that,
so
right?
it's not that, but this is a generic thing for certain. So if you take a certain recurring surface, you always have a log square. The difference we have here is that because of the network, you have a log square. So there's a log square direction to this log, because of the network, the third surface, because of this one on so important thing. And then if you put the chain like this in this direction, then you have one of the parts of the formula, then generic for spherical function. But I think that's it. Our plan is out, but so it's a good question. We're always every time we do numerics, we're confronted to some kind of symmetry which may bias every time we do. You have always important, you have always that case somehow, you have some attraction because the system is etc. If you take the dimensional mismatch, right, with the conduction of one is higher than the spin chain, then you could argue that the fact that you're stuck with particles and magnetic bound, or that particle and magnetic production may not be detrimental to it. That's what we hope. It's also a way if you want, but this Fermi surface is unstable. All the Fermi surfaces you generate are unstable. You have repulsive interactions. They are always nested. They're always time. And so every time you have as many spins as conduction electrons, you will always open up the field out. That may be a big scale, that will spoil a lot of the physics. But if you keep this, you have to put a one-dimensional chain, then you really have the possibility to take the substances have metal.
Actually, just a quick thought. Actually, so it seems like by integrating out the Fermi surface, the time direction interaction is always the same power. But actually, suppose the Fermi surface has some Van Hoff singularity. Actually, the power can be different from two.
Yeah, that's what I was. Yeah, the power can be different in time or what in space.
Yeah, right. So
in time, it gives us this has a double. This has two Van Hoff singularities. It has a netting which is the law, and also has the Van Hoff singularity where the law equals to 0. Right. So this has a log square. Right? And so essentially this comes in the log square conversion to the time. But the change in the real space, decay is actually much more dramatic, right? It gives you a depending on how you feel, the power. Is that okay?
Okay.
For the log, you don't use your simulation.
No. We don't use any. No, we don't use models. The log is.
So you should, but it's maybe small effects.
It's small. You don't use it.
And for this would be for the experiment, they have 9 How about that one? But can you see some of the physics already with 9 experiments, or how do you compare your phase diagram with
But for the moment, I don't think so. There's still, I think that's the wrong threshold. If we know we're doing those simulations, we have made it, one line to development. We see things that's not happening. I think there's no overvalued, is still very strong. So that's the, so it's a bit tricky. You don't have to go much further. I mean, the results, our research only work, these are small systems, we're looking at, the 44 and 44 degrees.
For the square lattice.
Yeah, okay, I guess it's very nice. There have been some, I don't know, I'm not going to say that, but there's some beautiful, graphene and stuff and more than the black. What the thing is, when I learned it's finished, not too far away, 44, where you see some like physics. So they got,
Yeah, I had a question about the star phases that you mentioned. And I was wondering how the parsons which are using one dimension less contribute to the volume of the funding. So is it
okay. So there's an argument for this program. So the fermion. Okay, so I guess your question is how do I define every fermion and how do I define the breakdown of my logic?
Yeah, exactly.
So that's pretty easy actually. There is an appendix in one of those papers there's an answer to that. That's the following. This take this is my unit cell. Right? My unit cell is just I have transition into one image. So it's like the most one of the problem. And so the heavy fermion phase, you're determined. So the heavy fermion phase is basically go ahead and have atoms. So the unit cell is a conventional electron that is not another electron. Right? The heavy fermion phase has alpha one, right? Because I have the plus one electron in the center. That gives me an alpha. And then the Kondo breakdown phase basically has just count because it's not just one. So you can really, of course, it's a bit tricky because it's sub-intensive, right? Yeah, I do a calculation on something. But on any finite count, you can go this idea. So I'm not going to the thermodynamic. Yeah, we're going around.
So the other question is, so the quantum problem that you find together, it seems to have a single species of the fractional, right? There's one fermion.
Yeah, it's like the easy solvable, single species.
Yeah, so I was just wondering, so like the spin operator, which
When we think of these, this is the spin on, so there is two spin on. There are two up and down.
yeah. So I was wondering, like, the spin on is the fixed speed, right? And what we have on the right side, the spin operator, the spin on is two spins create one speed.
Yeah. So the polynomial of this gives me a spin on. Single spin.
But in that relation, it appears that the spin operator on the right hand side, that means one spin on.
Yeah, it basically is, if you want to terminology, this will be a spin on, you don't spin on with the things that you go with. And then you get a full spin and a full charge. This is in my this is a one charge, you want to overcome the electrical charge. This thing gives you the electrical. And then you have all
Is it between all scenarios? Is it an operator identity or is it only applicable to certain phases?
So this is an operator identity that could be any type of formalized model of the so that's it's also very nice, because technically measuring this object is a thing, right? So if you want to measure correlation function with this
Another question. So to make sure I understand, so you did two simulations, right? You did simulations with all the fermions in the spin, and then you did simulations of expected.
Right.
Sort of quadratic.
Right.
So I was wondering, in the first simulation, did you look at sort of the fermion properties away from the two visible? For example, if it's something like a color screening cloud, you only measure properties along the chain.
You just measure the local property along the sheet. I mean, in principle, the Kondo screen, so you just measure things along. Well, no, we have some data which is the way we can. So,
Like in the SDN, do they measure away from the?
yeah, but that's when they measure all the Kondo. I can go far away, let's see. You can go and see. So that, but for the Kondo screen problem, that's, you could measure the correlation. And so you can measure, of course, you can measure statistical correlations when you should use it. Like say,
Just that way you go, but away from the chain, you know, you start a tunnel.
you can, it's always, I mean, at the end, you can tunnel on top of the pole lines, the resonance, and go away from it.
Well, there's,
And so,
there must be some.
so here's, but of course, it's not a step, right? It's not a step, right? And so, it's part of the state, you have to learn. So you could try to, okay, so you could try to define,
Especially if you're.
yeah, you could do, the problem is that this composite term, I can only define it at the position where I hybridize. That's the problem.
No, but I just mean the back action on the remaining real fermions that are.
Right. Yeah, but if you try to calculate the spectrum, yeah, but this is like, so if you did just have the spectrum, local spectrum function, yeah. The problem is that you don't have such a nice signal. The common reference when someone through the conduction of it, basically the whole conduction that's what makes a little bit. And it's hard to resolve compared to the very much smaller units of people. Like very critical.
If you're the critical point, you discuss things that leak out and some.
Well, they will always be down to measure, right? They've always been down. There's no getting rid of events.
Yeah, I think that's what.
But there's a change. So there will be a change in all of that.
Put down anchor gallery.
Yeah.
But it's more difficult.
Fakher, actually, I have a simple question.
Yeah.
Maybe it's because of acoustic. Maybe I found if you stay close to your laptop, I hear you more clearly.
The microphone, this one.
Yeah,
Can you
yeah,
hear
yeah.
me
That's better.
Okay.
Yeah, yeah. That's so the question was that for the first part, you have this antiferromagnetic metal. You have this Kondo heavy fermion metal.
Right.
Did you really see? I mean, is a Kondo fermion metal actually breaks Latinger counting?
Okay, so it's a.
I think it was related with one of the questions.
Yeah, it was, yeah. So the claim is no. So you have to define Latinger counting for these problems. Zion,
Right.
And so the answer was if you take your system and you have a translation symmetry along the chain. Okay.
Mhm.
So your unit cell has one spin and L conduction electrons.
Mhm.
Right. And so the Latinger counting would be L conduction electron plus this composite fermion. And the claim is that across the transition, because we see the composite fermion, which is still there, that the Latinger count does not change when you go from into two phases.
Mhm.
That's the point. Of course, it's a bit tricky because if you have long range order, then the unit cell doubles, right? And so you have to redefine the Latinger count. All these things are a bit tricky, but there's no Kondo breakdown in that sense.
Mhm.
In the other case here, that is this case here where you put in you look at the a Dirac system instead of a Latinger instead of a full Fermi surface, then you can
Right.
really see that there is a Kondo breakdown, that this particle disappears at the critical point.
Right. Right.
Composite Fermi. So
Uh-huh.
that would be a breakdown. That would be somehow a violation of Latinger
Right.
volume. If you
Right.
there should be L+1 particles per unit cell, and then suddenly there's only L. There are only L.
Mhm.
That's well, that can be, so the point is that even in those dimensional mismatch systems, you can define well the notion of heavy fermion,
Yes.
and you can
certainly, yeah.
define well the notion of Kondo breakdown. That's something which you can define well.
Okay. Yeah. Thank you.
What is Dirac? Putting the C fermions in a Dirac
Yeah.
structure?
Yeah.
So you write fermi liquid star. So there's just like a Dirac liquid star or.
So the fermion liquid star, that's what I'm saying. It's it's a violation of Lessons of all. Right, basically what, so you can debate if this is a good answer or not.
We have a KF or not in this phase, FL star, your FL star, the Dirac is pretty,
Well, okay,
fine for instance.
no, it's a point, it's what they say. Point.
Yes, we will, notation with the Dirac star, like Dirac liquid star.
Because the turnover is a change,
Yeah.
so you have basically, it's a phase with violation of the bond. So you would have to, because you have because you should count the fermion, the spin should be counted in the relative volume.
Right.
So you have to find that, so the understanding is that you have to find out the spin-offs.
For the spin-offs have a KF. They have
Yeah,
a-
spin-off, yes, they have a KF.
There's a KF singularity.
It's a two gas singularity spin. So in this phase, I mean, I don't want to bore you guys, but in this phase, if I can get my, oh, what happened here? In this phase, it's remarkable to see that the two spin-on continuum. So if you look at, can you see my screen? No. Can you see, how do I get back to the Zoom? Yeah, I know. I just have to find my screen, my Zoom thing, right? That's good. I'll just share the whole thing. You can see that again now, correct? This is the result for the Dirac system. Right? So there's a transition around. So this is the spin chain element. Right? This is the spin chain which is Kondo coupled to the Dirac system at JK1.5, which is pretty big. And you still see this very nice two spin on. So that you should compare this to the other cable we have, when you really have the case square. Right, so that's telling you somehow that you switch on the JK, you switch on the coupling, but the spin system is the spin system.
It's already in single impurity problem, coupled to a correct point.
Yeah, that's
There's a critical JK.
yes, yeah. So,
Similar.
but it's I agree, but you would not be able to show that. It's an intuition, right? But
For a single.
but going from the single impurity
Yeah.
to others, that's not true.
No, but I'm saying it's
No,
not.
it's similar.
Yeah,
Yeah, right.
Decouples.
Right. So okay. So this whole, so you can say this way, sort of it's a generalization of the sort of pseudo gap on the that would be a generalization of pseudo gap on. And you can also see, that this composite fermion thing, right, also breaks down. This is the magnitude of the composite fermion. The spectral rate of the composite fermion, anyway, you see that you didn't have this pole. But that's you have these two type of transitions.
Okay, very good. So I think we'll stop here and let's thank Fakher for a great talk and brief.